Alright, now let's continue further, and now let's look at problem 7. And so it has, let's see, how many parts is it? 6 parts. So it's part A says, show that for x times y is not equal to 1, that arctan of x minus arctan of y is equal to x minus y divided by 1 plus xy. If the left side lies between negative pi over 2 and pi over 2 and positive pi over 2. And then part B says, show that arctan 120 divided by 119 minus arctan 1 divided by 239 is equal to pi over 4. And then part C says, deduce the following formula of John Machin, or Machin. He was born 1680, died 1751. Of 4 times arctan 1 over 5 minus arctan 1 divided by 239 and equals to pi over 4. So deduce from that. And then part D says, use the Maclaurin series for arctan to show that arctan 1 over 5 is between this right here, 0.197395557. And over here, 0.19739555616. Then part E says, show that arctan of 1 divided by 239 is between this number. So 0.0041840075 and 0.0041840077. And then lastly, part F, deduce that correct to 7 decimal places, pi equals to 3.1415927, and Machin used this method in 1706 to find pi correct to 100 decimal places. Fascinating. So recently, with the aid of computers, the value of pi has been computed to increasingly greater accuracy. In 2009, T. Daisuk and his team computed the value of pi to more than 2 trillion decimal places. Fascinating. Alright, so now let's take a look at the solution to part A. So part A says, show that for xy is not equal to 1, and you have arctan x minus arctan y equals x minus y divided by 1 plus xy. If the left side is between negative pi over 2 and pi over 2. So let's just write this out. Arctan x minus arctan y equals to arctan x minus y over 1 plus xy. Yeah, just scroll up here. So arctan x minus arctan y equals x minus y divided by 1 plus xy. And just recall the definition of arctangent, or just whenever you're dealing with this arc or this inverse tangent or inverse trigonometry. So if you have something like this, a triangle, here's the theta. So that's theta. If you have opposite right here, opposite, and then you have adjacent. And we're dealing with tangent. So tan theta is equal to opposite over adjacent, just a general definition. This means that, well, the arctan of the ratio opposite over adjacent is equal to theta. So basically, you're looking at the inverse of it. So you're solving for the theta. So when you have theta, that's the arctangent there. Alright, so now let's start off with this. Now that we have that, so let A equals to arctan of x and B equals arctan of y. So then this formula that we're trying to show, basically show that A minus B is equal to arctan of x minus y. X minus y over 1 plus xy. So that is what we want to show. So show... show this one. Or just move it over and write, show that A minus B of, equals to arctan x minus y divided by 1 plus xy. And now if we compare this that we're asked to show with this right here, well, we could see that arctan, this is the opposite over adjacent, and this is the theta, is right over here. So this is equal to our theta. I'll just put a theta right there. And similarly, you could write this this trig identity right here as tan of a minus b equals to x minus y, 1 plus xy, where this is, that is theta. Yeah, so basically this is exactly what we need to prove. So basically we can now use the trig identity for tan a minus b and then try to prove that it's this. And then hence we've proven our identity that we're asked to prove. Alright, so now continuing further, so recall the earlier formula I referenced above in the, I think the other question. And now take a look right here. Yeah, so we had tan x plus y is equal to this, and this is tan x minus y equals to this tan x minus y, and then divided by 1 plus tan x tan y. And we're going to use this identity, throw that inside, and basically try to prove that it's equal to x minus y, 1 plus xy. So let's jump right ahead and do that. So using the second formula we have tan of a minus b is equal to tan a. So instead of x we use a, instead of b we use y. Tan a minus tan b over 1 plus tan a tan b. And now we could plug in our a and our b's. Number a is equal to arctan x, and b we let it equal to arctan y. So that means this equals to tan of arctan x minus tan of arctan of y. I'll divide this by 1 plus tan arctan x times it by tan arctan of y. And now that we have this, note that when we do a tan of an arctan of x, this actually cancels out equals to x. This whole thing becomes x. This is just x. And this right here is going to become y, and we'll go over that in a bit. This becomes x. This is y, and I'll just do a brief breakdown. So recall. Yeah, so recall again. It's when you look at the inverse trig definitions, with the regular definitions of trig, they all just match up. All right. So here, if you just draw a triangle, so let's say you had opposite at x, and then adjacent is 1, and you had an angle theta like this. So we have tan theta is equal to OP, opposite over adjacent, equals to x over 1 equals to x, right here. So it's equal to x. And we know that, well, when you take the inverse, theta is equal to arctan of x. So the arctan of the opposite over there equals to, so this is arctan of x. Yeah, so then what that means is, well, we could just plug in this theta inside. And again, this is by definition, this is the opposite of this one. So it's the arctan of the opposite over adjacent. So then what it becomes is tan of arctan of x. So plug that theta inside. This equals to x. That's just over here. So in other words, tan of the arctan becomes whatever is inside there. So we could just replace that over here with y, this one with x, this with y, etc. So, so what we have is, well, let's just throw this over here and write thus. And if you've listened to my earlier videos in this video, you'll see my favorite word is thus. So thus, we'll have here tan. So thus tan of, I'll put this, better. Tan of a minus b equals 2, and we have x minus y, 1 plus xy. X minus y, 1 divided by 1 plus xy. And now when we take the arctan of this, take the inverse, so then this means a minus b is equal to arctan of x minus y divided by 1 plus xy. And we know that a and b, well, a is equal to, just put it all together, arctan of x, that's a, and then minus arctan of y, that's b. this equals to arctan of x minus y over 1 plus xy. And just bold this out or circle it, and that is our identity. And yeah, so look at this one. If you scroll back up to the question, and we'll see that, yeah, that's exactly it. So arctan x minus arctan y is equal to x minus y divided by 1 plus xy. And note that this identity is for xy is not equal to 1, and also the left side lies between negative pi over 2 and pi over 2. And we can show that. We'll go over here further. That's because, again, we're dealing with this tan a minus b. And I'm just going to put this for xy is not equal to 1. Yes, and continue further. So note that the left side is between negative pi over 2 and pi over 2, again, because we're dealing with this tan a minus b. So if we have, let's say, I'll just say recall. Well, first we have tan of, I'll just do theta. Like this, I'll just draw it like this, actually. So let's say we have our angle, theta, where theta is equal to a minus b. Because remember, yeah, a minus b is just a tan. It could be viewed as the angle inside this tan. And remember that this goes up like this. This is the asymptote line here, and this is our tan theta. Tan theta. And then going this way, this goes back downwards like that. And this is our asymptote line. This is at pi over 2. This is at negative pi over 2. So that's where the tan function is applicable for here, negative pi over 2. And here I just moved it over to this side. So that's this asymptote line at negative pi over 2. And then this is a periodic, so it keeps repeating. But since we're doing the inverse or the arctan, I'm going to get a drawing right here. And it's drawn in red. So let's draw in red. So recall that the inverse of this would be, well, we just switch everywhere. So instead of this going to infinity at pi over 2, you instead are going to pi over 2 at infinity. So this goes here. And then so we just inverse everything. Draw it like this. This asymptote line now is pi over 2 for the inverse. This is arctan theta. And then similarly, this goes like this. Oops, it's actually under. And it keeps going on and on all the way until infinity there. Let's try this a bit better. Okay, so it goes like that, and then this asymptote line never reaches it. Just keeps going and on and on and on. This is going to be our, I'll just keep going. This is our negative pi over 2. Yeah, so what we have is arctan theta never reaches beyond pi over 2 and negative pi over 2, and that's by taking the inverse of just the first periodic cycle of this tan theta. And you can't keep going more, otherwise you're going to have a non-one-to-one function. Basically, you'll have this stacked up on top vertically, then for every theta you'll have multiple arctan, or every arctan theta value here, because then you'll have, when you're inversing, this will be the opposite over adjacent, etc. This will be the theta sign. But anyways, so this is, for the arctan. We just do the first cycle, and we have one function like that. Yeah, so thus, what we have is theta is less than pi over 2, and, so theta is between negative pi over 2 and pi over 2, like that. Where theta is just our, so let's go pi over 2, a minus b. So the left side is going to be between pi over 2 and pi over 2, like that. And that is the, quote, left side. Let's put quotations like that. That's just left side right here. Alright, and now the last thing to check is just that, note that if xy is equal to 1, so here we have it not equal to 1, because if it is equal to 1, then what we'll have is, well, rearrange it, y equals to 1 over x. And then what we have is our a minus b is equal to arctan of x minus arctan of 1 over x, like that. And we could even plug in the full formula, but it doesn't matter there. It's going to be the same thing. So the issue with here is at x equals to 0, we're going to have a arctan of 0 minus an arctan arctan of 1 over 0, which is going to infinity. 1 over 0, in other words, we're having an arc, it's approaching arctan of 0. And also, arctan of 0, that is just, arctan of 0 is just 0. That's just 0 there. So it's approaching, well, 0 minus arctan of 1 over, that's going to infinity. Let's go arctan infinity. And this is approaching 0, we'll just remove the 0, minus, and then when you go to infinity here, you're going towards pi over 2. I'll just go negative pi over 2. Like that. Yeah, so you're going negative pi over 2, but this is, so it's approaching that. But the thing is, or it equals to that when you go into infinity, but we can't equal to this, so it's between that. Yeah, and it's also infinite, that you can't have an infinite there, so yeah, we're not actually there. And I'll just say, but you never actually reach it, and then you'll just say negative pi over 2 is greater than a minus b. So you can't have it equal to that, you're going to have an infinity, and you're also approaching this pi over 2, which you can't actually, which the left side is never actually going to ever reach. So anyways, yeah, so we can't have undefined stuff in the equation there. So we can't have this undefined even if you solve this, and this will also be the same thing. So anyway, so it's not equal to 1 there. And I'll just write this for completeness. This is undefined. Yeah, the solutions manual just assumed all this. They didn't even talk about this equals to 1 there, or not. Yeah, what happens when it's equal to 1. Alright, so now let's jump right ahead to solution to the question B. So let's recall question B, or part B right here. It says, show that arctan 120 divided by 119 or 119 minus arctan 1 divided by 239 is equal to pi over 4. So let's just throw in those numbers there. So we have, from A we have arctan, right, our formula we proved, arctan of x minus arctan of y is equal to arctan of x minus y over, or let's remove the bracket, x minus y over 1 plus x y. And now we're going to replace x with, let's see, arctan of, and scroll back quickly again, it's going to be 120 over 119, 120 over 119, and then 1 over 239 equals pi over 4. So let's go back here, 120 over 119 minus arctan of 1 over 239. This equals to, so we have that. Now we can just add those terms. Arctan of 120, or this is 120 over 119 minus 1 over 239, and then divided by 1 plus 120, 119 times it by 1 over 239. All right. Alright, so now we're just going to do a bunch of algebra and solve this. We need to show that this is equal to pi over 4. And what I'll do is throw this inside. And let's do this. So 120 over 119 minus 1 over 239. Yeah, like that. Divide this by 1 plus 120 over 119 times by 1 over 239. And multiply this by the common denominator that we want is 119 over there, and we're going to divide by that as well. So, and that's at the bottom, so we'll just get multiplied and get it all canceled out. So 119 times it by 239, divide this by 119 times 239. And now we're going to get a bunch of cancellations. And this is going to be, well, when you multiply this inside to this left side here, the 119 cancels. So we're going to get a 120 times it by 239. And this one, the 239 cancels, and then we're left with this 119 minus 119. Then the bottom, this whole thing at the bottom cancels, so we're left with a 119 multiplied by the 1 here, times 239, and then plus just a 120. And now, instead of just putting this in a calculator, let's just do some algebra. So this equals 2, and I'm going to factor out this 120 into a 119 plus 1 times by 239 minus 119 all over 119 times 239 plus 120. Just so we have the same common denominator, multiply this inside. This equals to 119 multiplied by 239, and then plus this extra right there, 1 times 239, so 239 minus 119, like that. And this is a 119 times 239. Notice they match up, plus a 120. And now if we subtract these, this is 239. Alright, yeah, so just subtract the 239, just do long subtraction, 119. So subtract that, this cancels, we get a 0. So it goes a 0, and then actually I just remove those lines, you don't need to cancel, just put a 0 there. 3 minus 1 is 2, then 2 minus 1 is 120. So in other words, that equals to 120. Yeah, so put this all together, we got a 119 times 239, and then plus 120 over 119 times 239, and then this is plus 120. So they all just cancel, and we're left with equals to 1, which is quite fascinating. And now here's do a quick calculation check. So MES calculation check, 120 times 239 minus 119. This equals 2, and then it's built in OneNote, just press space, auto calculates, and so on. Same with this. This will get a 28,561, then 28,561 over there. And that is just this part right here. And then this part is the bottom one. And then you'll see it's the exact same thing, so those obviously cancel. And you can also just do it from the very start without actually any of these manipulations. So 120 divided by 119 minus 1 divided by 239. And then divide that all out by 1 plus 120 times 119 times by 1 divided by 239, which is this. And you could see, press space, it equals to 1, which is quite fascinating. So now that we have this equals to 1, and we could throw that inside there. And when we throw that in there, so this whole thing becomes 1, and then we can recall our exact trig ratios. And so first, let's write thus. Thus arctan of 120 over 119, that's our x, minus arctan over 1 over 239. This equals to arctan of 1. And remember what this means. When you have arctan, you're dealing with the angle. Whereas this inside number, that's the ratio opposite over adjacent. So if we draw a triangle, this is going to be, so a triangle with like this, if it has opposite 1 and adjacent 1, that means this is just a square. So that's just a square with opposite 1. Yeah, so this is just a square, so that means this is divide this by 2. So the full angle is pi over 2. So this is pi over 4. So in other words, 45 degrees angle there. And likewise, this is pi over 4. So this is right angle like that, pi over 4. And that means, yeah, that's pi over 4, so that's the angle. So that means tan of pi over 4 is equal to 1 over 1 equals to 1. So again, opposite over adjacent. And this means now we take the inverse. So arctan of 1 is equal to pi over 4. So we just solved it like that. So this whole thing is equal to pi over 4 like that. So yes, quite fascinating. And now let's move on to question C. So scroll up there. So question C says, deduce the following formula of John Machin, 1680 to 1751. And this is 4 arctan 1 over 5 minus arctan 1 divided by 239 equals pi over 4. So essentially, basically, we're going to try to switch this up with this because everything else is the exact same. This is 1 over 239. This is 1 over 239. This is 120 over 119. So we got to write that as 4 arctan 1 over 5 if we can. And they do this just so that there's only 1 on the top. And this is 239. There's nothing on top, just 1. This one's a 120. It looks a bit off. So this is simplified. So let's continue further. So we are asked to show, that 4 arctan 1 over 5, write this better, 1 over 5 minus arctan 1 over 239 is equal to pi over 4. Alright, so now to try to demonstrate this, first notice that this has a 4 there, so that means we're adding up arctan setups. So what we'll do is so the solution manual does this. So it replaces y by negative y in the formula of part A. And recall the formula of part A. That is just this part right here. Arctan of x minus arctan of y equals to arctan x minus y, and then divided by 1 plus x y. So it replaces that so that we'll have an addition here. So the idea is to have an addition. So we'll have a 2 arctan, etc. plus this, and so on. So let's continue on, and we'll start to make sense. So arctan of x is equal or minus arctan of negative y, and this equals to arctan of and then this is from the formula of x minus negative y, like that, and then divided by 1 plus x times y, but it's negative y now, like that. Alright, so we have this. Now this setup right here, this is equal to, this part right here, is equal to a negative, this is equal to negative arctan of y. And we'll show that. And yeah, we'll show that, and the reason, so then we're going to have an addition there. So we're going to show that because, well, recall that if we have a triangle like this, let's say we have a triangle, again, a right angle triangle, and when we're dealing with tan, we're doing opposite over adjacent. Let's say we have y here, and let's say this side length is 1. So this is the angle theta. So tan of theta equals opposite over adjacent, so y over 1, like that. Yeah, so thus the arc length is going to be, well, or theta is going to equal to arctan of y. But now if we have the negative y, that means the opposite side is going to be negative. So like this. So this would be all the way down. So if this is still positive, you have a negative y like that. And this is going to be negative theta. So that's angles theta. This is going to be negative theta if that's the starting point over there. Yeah, so that's what we have there. So that means tan of negative theta. So negative theta is equal to negative y over 1. So this means that, so we're going to get a negative theta is equal to, arctan of negative y. Yes, so that's equals to this, and where this theta is just this, so we could plug that in. So then basically what we'll have is arctan of negative theta is equal to negative arctan theta. So negative theta, which is just equal to a negative arctan y there. Yeah, so negative arctan y. So throw that whole thing in there. So we can box this out. So basically, this whole thing, arctan of negative y is equal to negative arctan y. So put that inside, throw this in, thus, all right, yeah, so thus we have is arctan of x. So I'll write this out, thus arctan of x plus arctan of y, of negative y. I mean, not negative y. Negative y becomes this whole negative arctan y. So arctan y, and then equals to, and then do some simplification. This negative times negative becomes positive. So we'll have a x plus y over 1 minus xy. So we basically switch the signs there. So this is plus x times negative y, so it's minus, and this one's negative times negative, it's plus. So that is what we have there, which is quite fascinating. All right, so now, yeah, we have this, and again, we did this so that we can, and yeah, also, yeah, forgot to put the arctan of x here. So yes, lots of writing. Arctan of that, so arctan, then over there. So yes, so we did this so that we can use addition in the formula we are asked to show, and let's go over that again. Yes, so we are asked to show right here. So 4 arctan 1 over 5 minus r over here, but we're only worried about this one. So we could use that addition identity, separate this up, and the goal is to make it match up with this arctan 120 over 119. Yes, so let's just write that out. So again, where's this 4 arctan 1 over 5? All right, so let's write that down. So we could, so again, we did this so that we can use addition in the formula we are asked to show. So let's do the first part. 4 arctan 1 over 5 is equal to 2 arctan. So again, we've removed one of, so we simplify this 4 to a 2. So eventually we're going to do this again, so it's a 1. 1 over 5 plus 2 arctan 1 over 5. Now this equals to, right over here, arctan, but this is going to be a 2 there. So 2 times arctan of x plus y is, again, y and x are the same. 1 plus 5 plus, yeah, it's then plus 1 plus 5 like that. Divided by 1 minus 1 over 5 times by 1 over 5. And what we'll do now is, well, inside this arctan, I'm going to multiply the top and bottom by 5 squared over 5 squared, like that. So we get rid of all these 5 squared. So mainly this one, get rid of that. So this equals to 2 times arctan, like this. And then 1 over 5 times 5 squared, that just gets 5 plus 5, like this. And then the bottom becomes, well, this is 25, like that. So 25 is just 5 squared, 5 times 5. And then minus, this all just cancels, becomes a minus 1. So then this equals to 2 arctan of 10 over 25 minus 1 is 24, like that. And let's simplify this further. We could cancel this as it becomes divided by 2 is 5, divided by 2 is 12. So in other words, yeah, this equals 2 arctan 5 over 12. And let's box this, and then we're going to do the repeat again. So repeat, like this. I'm going to put this like this. Repeat, the same setup, using the same identity, so we can use the same addition one. And we're going to get a 2 arctan of 5 over 12 is equal to arctan of 5 over 12 plus arctan of 5 over 12 equals to arctan, and then we had x plus y, then divided by 1 minus x y. So we'll have a 5 over 12, or actually here I just moved it over to this bottom right here, so this becomes, so I'll just make this a bit bigger. So 5 over 112 plus 5 over 112 divided by 1 minus 5 over 12 times 5 over 12. Alright, so now multiply top and bottom again by this exact same setup as we did earlier, 5 over 12, and then we're going to square this. And this is 5 over 12 squared. And we'll do some cancellation. And yeah, actually I made a mistake here. Yeah, so notice this one here we multiplied by the above it. So this is 1 over 5 multiplied by 5 there. So here we got to multiply, flip these upside down. 12 over 5 and 12 over 5. So then we'll have cancellations. This equals to arctan of, and then this will cancel one time, and then we'll just be left with a 5 over 12, and then plus, I mean not a 5 over 12, well, because we're doing this, we'll cancel out, we're just left with this by itself, so 12 over 5, it's the exact same setup as before, 12 over 5, And then this is going to be subtracted by, this whole thing cancels. Well, this whole thing, and this one is just a 1, so 12 squared over 5 squared minus, and now this all cancels, minus 1. And now we'll do this again. Now we have a 5 at the bottom, and there's a 5 squared there. Multiply the top and bottom by 5 squared over 5 squared. Alright, now we'll do some more cancellations, and this equals 2. Well, 12, the 5 cancels, we're left with 1 5 there. So arctan of 12 times 5 plus 12 times 5, like that, and then this then divide this out. This becomes 12 squared, and then this this 5 cancels, 5 squared cancels, and this minus 5 squared. And now simplify this one further. So this 12, this 12 times 5, you could factor out the 12s. So then this is, let's put this like this, 12 over 5 plus 5 equals 1210. Yeah, so we'll just write this complete down. So 12 times 10 over this one here, 12 squared is 144, so recall that. And then minus 5 squared is 25. So the only thing we need to do is, well, right here, this is 144, and this part here is 120 there. 144 minus 25. Yeah, so, alright, so like that. And then minus this would be a 14. Minus this is a 9. And then this cancels, be 3, because we had carry that. We added a 10, so we have to subtract 1. So this can be a 1. And then right here, 1 minus 0 is just 1. And right here is going to be equal to, well, actually before that, again, we forgot to put the arctan there. So move this to this side. And this is arctan. It's kind of like when you're doing limits, you also need to put the limit sign at all times. Alright, so we have that. This top part is just 120. Like that, or yeah, so that's just 120. So now what we're going to get is equal to arctan of 120 over 119. And yeah, this is quite amazing, do all that. Alright, so thus, from part B, we have, so put this all together, 4 arctan 1 over 5 minus arctan 1 over 239. This equals to, well, this part is just this. So this equals to arctan 120 over 119. Again, that's just from part B. 119 minus arctan of 1 over 239. And from part B, this just equals to pi over 4. Like that. So yes, fascinating. Alright, yeah, so that is part C. So now let's look at the solution to question D. So let's scroll up to question D. And let's go back up here. And again, note here. So this is for question C. 4 arctan 1 over 5. We show that it equals to this. And then we already showed that this equals to pi over 4. So combine that all together. So now part D says, use the Maclaurin series for arctan to show that arctan 1 over 5 is between this setup. And let's just go over to the table and recall the arctan. See how far we have to go to get the table. Alright, here, so we teleported across here, and here's that Maclaurin series. This is arctan. It's the same thing as writing tan, inverse tan, or tan negative 1x. The same thing as writing arctan. So that is that. And this is the series. The Maclaurin series go to x minus x cubed over 3 plus x5 over 5. So it's odd powers and odd factor. I mean, there's no factorials. Odd powers and odd divisors or denominators. And they match, and there starts from x to the 1, and it goes from minus plus, and its r is equals to 1, the radius of convergence. Alright, let's go back all the way down. Alright, and now we're asked to show that it's in between these two range, so we're going to have to sum up that series, and this is arctan 1 over 5. Alright, so let's go over there, and we're going to be using part C, which had a 4 arctan 1 over 5 there, so that's at 1 over 5, and so on, and eventually use it to estimate pi. Alright, so recall from the earlier table above, or here, solution to D. So we are asked to use the Maclaurin series for arctan to show that arctan 1/5 is between this number 0.19739, etc. all the way, and then it's less than, it shows greater than this, but it's less than 0.1973955,616. This one has a 55597. So very, very accurate. We need to get it to. So recall from the earlier table above, tan inverse tan of x, or tan -1 of x, it's the same thing as arctan. It's just different ways of writing the exact same setup. Arctan of x equals to an arc. I think it's arc. They say this because it's like the arc of the angle. So it's the angle or the arc there. So arctan of x, this equals to number odd. Power starts from x to the 1 minus x3 over 5 plus, over 3. So they match up, plus x5 over 5 minus x7 over 7. And then it goes from plus minus ... And r, radius of convergence, is equal to 1. Alright, so now let's plug in our 1/5. So we're asked to go 1/5 there, so x is 1/5. So thus, we'll have in our case arc tan of 1/5 is equal to 1/5. So 1/5 minus, and then there's the x's there. This becomes 1/5 cubed, or before we get to that, I'm just going to write 1/3 times it by 5 cubed. And then plus 1/5 times 5 to the power 5. Because this is 1/5 to the power 5. Next one is going to be 1/7. So let's put a 7 there, times it by 5 to the 7. And then it keeps going on and on. Plus, minus, ... Alright, so now that we have this set up here, note that this is just an alternating series, so it's switching from minus, plus, and the size of the terms decreases to 0. So notice how it's getting bigger and bigger at the bottom. Eventually you're going to go 5 to the infinity at the bottom, and so you're dividing it, it's going to approach 0. So we can apply the alternating series estimation theorem as recap from my earlier video below, as well as on alternating series test and so on. So note, if the alternating series is for the alternating series test, summation from n equals 1 to infinity of -1 to the power of n minus 1 bn equals to b1 minus b2 plus b3, where bn is greater than 0, similar to ours. So this is, or bn is greater than 0, and it's alternating, the terms are alternating from positive, negative, etc. Positive, negative, and satisfies that bn plus 1 is less than or equal to bn. So notice that each of the bn's are getting smaller and smaller. So this is going to be, you're dividing by bigger and bigger number. So I is true for all, and the limit as n approaches infinity of bn is approaching 0. So this is approaching 0 there. Then the series is convergent. So this is a convergent series. And then, before giving the proof and so on, yeah, I'm just not going to go over that paragraph, but basically, if we recall this line graph, and yeah, here I just removed that initial paragraph just so it gets in the way. So I'm just going to look at this graph right here to show you how it converges, just to illustrate this. So, for example, at 0 right here, let's say the S1 here is going to be just the B1. And then you're going to subtract that by B1, which is getting smaller, by B2. So this is B1. And then you're going to subtract it by B2, which is getting smaller. So it's going to get somewhere at S2 here. Then you're going to add by B3, which is smaller than B2. So it's going to go somewhere across here, so S3. Then you're going to subtract again by B4, and that's smaller. And then again, it keeps getting smaller and smaller. Eventually, you're going to get to converge to a point here. So let's illustrate the alternating series and how it's convergent for when B is getting smaller and smaller and it's going to 0. And then alternating series estimation theorem, if S is equal to, so -1 power of n minus 1 bn, so this is just showing that it's alternating, is a sum of an alternating series, then that satisfies bn plus 1 is less than bn greater than 0, so each one's getting smaller and smaller. And limit goes to as n approaches infinity of bn is equal to 0. Then the remainder, r sub n is equal to s minus sn, so the actual sum minus the nth partial sum is going to be less than or equal to the next term bn plus 1. Yeah, so in other words, if we look at, let's say we had S5 there, and then we had the actual sum is here. This means that this is the remainder R5, and it's going to be less than, yeah, this one here, R5 is less than, well, the next one. The next one is this B6 there, less than B6, or the absolute value, or just, this is positive. Yeah, so it's less than that because notice how this one is much bigger than that, because this one goes all the way across this negative, this S1 there. And this happens each time. So even for S3, the difference right here, R from to S3, is less than this B4, which crosses that S. So yes, fascinating stuff. And that is what this note says. You can see this geometrically why the alternating series theorem is true by looking at the figure, this one right here. Notice that S minus S4 is less than B5, and absolute value of S minus S5 is less than B6, right there. And they use absolute value because in this case S is less than S5, and then, but if you have it on the even side, S is greater than S4, S6, etc. So those will be positive. On the right side will be negative. So anyways, alright, so that was recap on alternating series, the series test, and so on, and the estimation theorem. So the remainder is less than that, but also you could see that each S, so the S is always between, for example, S5, S6, it's always between S4, S3, and so on, and we just got to show that it's between this setup right here. And so what we could do is, so thus by the alternating series estimation theorem, the sum will be between each successive partial sum, and the error is the absolute value of the next term. So we're asked to show that arctan is between this. So first, if we put S1, this just equals to 1 over 5. So that's the first one. So it's S1 is 1 over 5. The next one's going to be 1 over, so the next S2 is going to be 1 over 5 minus 1 over 3 divided by 5 cubed. So that's this one. If you just put in the calculator, my OneNote calculator equals that. And then this one, 1 over 5 minus 1 over 3 times 5 cubed. This equals to this. Now S3 becomes this. But then, and this just, it's all rounded up. If you go S4, so 1 over 5 minus, so this is S3, and then minus 1 over 7 times 5 to the power of 7, etc. So we need to use a more powerful calculator. So here's going all the way here to using S5. S5 using Wolfram Alpha. Yeah, so Wolfram Alpha, a very powerful calculator website. So here, put that inside here, and we'll get this giant setup here. So 1 over 5, this is S5. So this is 1 over 5 minus 1 over 3 times 5 cubed, and so on all the way. This one is to the 9th one, or to the plus 1 over 9 times 5 ninths, and then it goes all the way here, and it even shows you the period where it repeats. So it starts repeating at the 6-5. So notice the 6-5 there, 6-5, and then each time it's 6-5, it repeats with 6 numbers, 6, 5, 0, 7, 9, 3. So that's very, very fascinating. So that is that, S5. And also note that the S5 says 1, 2, 3, 4, 5. This is a plus. So then the S6 will be less than, because we're going to subtract by it. So we're going to have the S6 is less than the sum, and S5 is greater than the sum. So anyways, keep going on. So then S6 using Wolfram Alpha, we get this. This is 19739555616. And this is 1973955, etc. 197. This is, so minus 1 over 11 times 5 to the power of 11. And we get all the way up to here. And so thus the sum lies between S5 and S6. So S6 is less than, because you have the subtraction term. So we have S6 is less than arctan 1 over 5, less than S5. So that means, that means arctan is less than, arctan 1 over 5 is less than, is greater than, all the way here, 197395597, and it's it's greater than, and it's less than this, and then here I have a ... just to stop just to match up with the question we were asked, and this is the up to here, just before that 8, so you have this exact, there's 3 5s, and the other one up top here is 55616, so here 5561, etc. And this is the same as that we were asked to show. And actually going back up here, this was 597. This one is also a 6 there. Just put a 6 there. We could see that right over here, 616, and so on. So this is the same as that we were asked to show. So we were asked to show this. I just copied and pasted it. I'm not going to go and check again. But yeah, so this is it. And it's the exact same. So note that the solution manual rounds up to, over here, they just round up 60. So 597. This becomes 60 right here. And it also rounds up 616, rounds it up to 62. So anyway, so that is what we've shown, just using that Wolfram alpha. So now let's take a look at solution to part E and scroll up to part E and see what it's asking us. So part E says show that, and then basically the same thing as this top one. Instead of arctan 1 over 5, we use arctan 1 over 2 to the, arctan 1 divided by 239 or 239 and show it's between these two setups. So let's go look at part E. All right, part E is right here. All right, so now solution to part E. So we are now asked to show that arctan 1 over 239 is between 0.00418, etc. And then it's less than 0.00418, etc. The only difference is 4075 is 4077. So basically 75 and 77. We got to show it's in between. So using the series in part D, we get, let's just write it out for completeness sake, and then we'll start using Wolfram alpha again. Arctan 1 over 239 is equal to 1 over 239 instead of 1 over 5. Then minus, this is going to be 1 over 3. Let's go 1 over 3 times 239 cubed plus 1 over 5 times 239 to the 5 minus 1 over, well, yeah, it keeps going on and on, etc. So minus plus, so that is a 1 minus, and then this is minus plus dot dot dot. All right, so now that we have this, and now since we are asked to determine the sum to 9 decimal places, so that was right over here. So this is 4, and that's 5, and then that's 9 decimal places. This is 9. That's 5 plus 4 is 9. We can calculate the corresponding remainder. So let's look at R2. So if we have R2 equals to S minus S2, so that's just right here. This is S2. So the actual sum minus S2 is equal to, and actually instead of regular brackets, this is absolute value because it could be negative. Yeah, so absolute value, and remove this. Yeah, so absolute value of S minus S2 is equal to B3, so the next term afterwards. So yeah, B3, so S minus S2 is less than or equal to Bn plus 1. That's the remainder. And again, this is less than or equal to sign, not, so add the symbol less than or equal to. So less than or equal to B3, which equals to 1 divided by, this would be the B3, 1 divided by 5 times 239 power 5. And then if you use my OneNote calculator, it's too small, so it just goes 0. So need to use a more powerful calculator. So if you use Wolfram alpha, and it gets to a 10 to the 13, negative 13. So that means this S2 is accurate to within 10 to the negative 13. So in other words, 13 decimal places, as opposed to what here we're just asked for 9. So that's going to be, so we could just use S2 as the number. Yeah, so the third term is less than 2.6. And here's rounded up rounded up to 2.6, 2.56, round up to 2.6 times 10 to the negative 13. Thus, by the alternating series estimation theorem, we can just use S2. So then if you use S2, that's just 1 over 239 minus 1 divided by 3 times 239 to the power of 3, and it equals this, again, using Wolfram alpha, and you get this 0.004184076, like there. So thus, S2 corresponds to the inequality we are asked to show. So S equals arctan 1 over 239 is approximately equal to S2, which equals to this, up to this 76. So 9 decimal places. This one, notice there's a 5 there we're asked to show, and 7. And this one is a 6. So it's in between these two. So arctan is in between these over here, because remember the remainders is very, very small. It's 13 decimal places as opposed to 9 right here. All right, so that is, yeah, so note we couldn't just use the inequality s minus, s between s1 and s2, because s1 is too large for the inequality we were asked to show. See if I could put this equals, yeah, this rounds it up. But if you use Wolfram alpha, it will show that it's equals to this. So yeah, S1 is 1 divided by 239. Put that in Wolfram alpha, you get this over here, 0.004184104. But then this is greater than the one we're asked to show. It's which is over here, 0.004184077. Yeah, because notice the 1 here. So that's this one right here, 4007. This is 41, so this is greater than that. And actually, here, because it's S2 is smaller than S1, this is, we'll have a reverse side. Let's go this right here. 2, 1, and then this one, 1. Whoops. 1, 2. Yeah, so we can't just use S is less than S1, and yeah, we can't use it less than S1 greater than S2. Yeah, because again, this S1 is too large for this one here. We're asked to show this. So we could just use the S2 then. All right, so now let's take a look at question F and scroll all the way back up. So yeah, this is a pretty tedious question, or tedious overall problem. So deduce that correct to 7 decimal places, pi is equal to 3.1415927, and then here's some historical notes. Machin used this method in 1706 to find pi correct to 100 decimal places, and recently with the aid of computers, the value of pi has been computed to increasingly greater accuracy. In 2009, T. Daisuk and his team computed the value of pi to more than 2 trillion decimal places. So here we're going to show it correct 7 decimal places over here, 3.1455927. So let's go over to here. And again, we could just use that, the formula we derived. So we're asked to show that. So then pi is, yeah, we're asked to show that pi is is approximately equal to 3.1415927, or basically accurate to 7 decimal places there. So from part C, we can deduce that. And we remember this one here. This is 4 arctan 1 over 5 minus arctan 1 over 239 is equal to pi over 4. So we had solved this earlier. Let's just go back up to show that. Just so we, yeah, just to show, because I was just using by memory. So we have over here 4 arctan 1 over 5 minus arctan 1 over 239 is equal to pi over 4. All right, so we have that, and we already calculated those, we already estimated those to very accurate figures. And yeah, going back here, so and since we're asked to solve for pi, we can just multiply everything by 4. So what we'll do is, well, multiply by 4, and we're going to get a pi is equal to 16. Yes, so 16, scroll up, equals to 16 times, yeah, 16 times arctan 1 over 5 minus minus 4 times 4 arctan 1 over 239. All right, here I just boxed this in, and now recall from part D, or parts D and E, the estimations we did. So arctan 1 over 5 is between this right here and this, and arctan 1 over 239 from part E is between this and this right here. Thus, we can apply each inequality into our formula for pi. So we want, yeah, so basically we'll take the pi as between, well, we'll take all the smaller number, or the numbers that give the smaller amount. So 16 times, we take the smaller one of arctan 1 over 5. That is this right here. So there's, notice the 97 there. Then minus 4, now we need to pick the bigger number because we're subtracting. So we put this one in. So this and this. This one goes into here, this one goes into here. So minus 4 times that, so it matches up with this arctan 1 over 239. and then is less than pi and less than 16 times. Now we get all the bigger numbers. So this is the bigger one here, 616. No, 616 at the end. And then minus 4 times a smaller number, which is this one here, because we have a negative. So 7575. So we do that, and what we get is, while calculating this out, we get, let's do the left side, 16 times this, minus 4, and then you could just use my OneNote calculator. Has it built in, per space, it goes to here. And likewise for the right side, per space equals to this, 3.14. And this is 7.2, this is 5.6. So in other words, pi is between this right here, and this is the decimal places here is, this is 4, 5, this is 10 decimal places. We only are rounding it to 7 decimal places, so we go 1, 2, 3, 4, 5, 6, 7. We get over here. Yeah, so we get over to the 647, and then here's 3.14 all the way to, let's see, 4, 1, 2, 3, 6, 8 right there, and then it's rounding up. We get a 6, and then this becomes a 7. So rounding to 7 decimal places, we get 3.14526. Pi equals to over here. Yeah, so we get pi is between this right here, 3.1415926, less than pi, it's greater than this, and it's less than 3.145927. And then the solutions manual use the upper bound. So using upper bound, we get the estimation pi is approximately equal to 3.1415927. And just another note here, calculation check. So let's go put it here. MES calculation check. Calculation check. So my OneNote has a built-in calculator. I could just type pi equals to, and it gets over it here. So that's an exact one. So 3.1459265. So there is the rounded part up. So those are the rounded up. So exactly this, get 27. Yeah, so here we have 5927. This is 59265. So rounded up to 7. So that is correct.